Yeah, so I'll give more like a general information about nanomaterials and nanotechnology.
Yes,
Gives few examples.
Yes, and I also want to inform you that this time the lecture is connected to the YouTube, so something
yeah.
Is that okay with you?
Yeah, sure. Yeah, you already told me that. Yeah, it's okay.
Oh, already
to
okay.
Upload it in YouTube. It's fine. That's okay.
Yeah, thank you very much. In our lab in analytical chemistry, especially, we also doing a lot of some nano material from modified electrode, some detector sensors and something, and some people also do a lot of nanosynthesis and everything. So I hope today the talk can be more. People will give more questions. I don't know. I hope it's fine with you. But this time I think this time I think I would like the student to talk by themselves. So I think this also can be helping them to try to asking question in English if that's okay.
Yeah, sure. Yeah, that's fine.
Okay. So I think since the time is already started, so maybe
share.
You can start whenever you want, because I think the students that come here today is also the same like before. So I think they already more or less. So
so I shared my screen. I think you can see it right now, right?
Yes, we can see it.
Okay.
Please,
so today I will. So today I will try to cover some materials about nanomaterials and their and nanotechnology and there's some specific applications and their specific applications. So I will give you some definitions related to nanotechnology, and I will try to give a sum up of some applications related to nanotechnology and nanomaterials. So there are some questions to be considered here. So what is the dimensions of a nanometer? So what a nanometer corresponds to in terms of size or dimension? What is a nanoparticle? What is nanoscience? So we hear a lot of nano these days, and different applications. You can see different applications, and you can see a lot of nanotechnology applications from different fields, like chemistry, engineering, even medical sciences. So these are all using nanotechnology, but they're pursuing completely different applications. They are developing technologies, but those technologies are completely in terms of working principles, but they're all called nanotechnology. So why we call them nanotechnology? So it's all behind the dimension of the some constituting elements in those technologies. So that's why we will try to understand the definition of nanometer and nanoparticle or nanotechnology, anything related to the name nano. We will also cover some opportunities using the nanotechnology, and also we will cover some critical problems, or even like some of the hazardous or some outcomes from nanotechnology that can harm human health, or even globally affect the Earth. So let's start with the definition of nano. So nano is a Greek word that means dwarf, so it's tiny. It's small. So it's 10 to the -9 meter, or 1/1,000,000th of a millimeter. So it's very small. So and here maybe you can go over the definition of nanotechnology. It's the understanding and control of the matter at dimension between 1 to 100 nanometer. So anything below a 100 nanometer, any technology that use elements, any type of elements that is below 100 nanometer, we can call these technologies nanotechnology. So the whole thing does not have to be in below 100 nanometer, but any constituting elements should be could be 100 nanometers. So one thing, I can give you one example. For example, let's think about a material below 100 nanometer, and you inject that material into human body, and you track that material. So even any infrastructure or any technology you use to monitor that material is big, like you cannot call them nano, because they're like devices such as microscope or any spectroscope, any devices you doing spectroscopic measurements, but the heart of that technology is that small material, that particle. That's why this application could be defined as a nanotechnology application. So let's think about the dimension of materials. So here a tennis ball is 10 to the 8 compared to 1 nanometer is 10 to the 8 nanometer. A tennis ball is, compared to a molecule, it's gigantic. So when you look at a water molecule, is 10 to the -1 nanometer, so it's like a 1 angstrom. So when you compare those tennis ball to a molecule, that there's a huge difference, like 10 to the 9 fold difference between the dimensions of these two materials. So today we will try to cover any biological or any non-biological materials smaller than 100 nanometer today. So let's continue with two definitions. Nanotechnology. So nanotechnology is the design, characterization, production, and application of structures, devices, and systems that can control to control shape and size of the materials in nanometer scale. Nanoscience is the study of the phenomenon and manipulation of materials at the nanometer scale, like atomic, molecular, or macromolecular scales. So when we really heard about anything about nanotechnology or any material in nanometer scale, it's 1959 by Richard Feynman, which is one of the most famous physicists in the world. So I wrote his quotation here. There is plenty of room at the bottom. So he's referring. So at that time, there were a lot of scientific development, but they were all in the micro scale, like signal and processing, like Einstein's theories, gravity, like a lot of development in an invention occurred till that time. But anything about like nanotechnology, that there was not really a fundamental development occurred in terms of nanotechnology. But he was referring that if you dig into the material worlds, like the nano world, you can find out new findings, even new phenomena, or there were even occasion that people realized, the scientists realized, anything applies in the macro world in terms of physics could not be applied in the in nano world. In another talk, he described a process in which scientists would be able to manipulate and control individual atoms and molecules. So in nanotechnology, what we do is we try to manipulate materials in nanoscales, and any variation in their properties, we can use those variations to understand the macro world using using the properties of the nanomaterials. So So we can look at more quotation from Feynman's talk, that I don't know how to do this on a small scale in a practical way, but I do know that computing machines are very large, they fill rooms. So why can't we make them very small, make them little wires, little elements, and little and elements, and by little I mean little. So it's 1959, and there was nothing we can really monitor, see, or manipulate materials in nanometer scale. That's why he's opening opening new doors for the for new understanding of matter in nanometer scale. So he's talking about how the phenomenon, the physical phenomenon known in that time, could change when we look at those phenomenon in nanometer scale. So the nanotechnology was found or invented by Professor Norio Taniguchi at the University of Tokyo in 1971. In 1981, with the development of STM, the scanning tunneling microscope, we can start to see individual atoms. Till that time, we couldn't really monitor anything about nanometer scale. What we could see is through, for example, like chemical reactions, or these type the interaction between atoms or molecules through by looking at their effects in microscale. So, but with the invention of the STM, we could really see what's going on in the nanometer scale. This technology has a tip that could almost touch to the nanomaterial, and between the interaction between that nanomaterial and the tip or the probe of this technology could give you the surface roughness of a material. For example, here the material at that time, the resolution of that material was around 2 angstrom, which gives you, when you think about, let's go back to this scale, this is about 1 angstrom. The molecule of that water molecule is 1 angstrom. So with this with this resolution, you can slightly see with this resolution you can see slightly larger molecules. So this technology really gives you the opportunity to see what's going on in the nanometer scale. So we already know nanometer scale is so in nature, in nanometer size materials takes important roles in nature. So this is the human organs in centimeter scales down to molecules in micrometer scale. Like micron is about like 10 to the -6 meter, and inside those cells there are thousands, millions of molecules, proteins, biological materials in nanometer scale. So let's give more example to understand the scale or the dimension of the molecule. So this is the eye of a fly. This is about 400 micron. It's like 4 times larger than the thickness of your hair. The thickness of hair is about like 100 micron. This is a red blood cell, about 10 micron, and this is the nanoparticles with the diameter of 50 nanometer. So when you compare those, so so you can fit I don't know how many 200 particles in a red blood cell. So you can make particles even that small. So as I told you, when you go from macro scale to nanoscale, things could change. In the and you can see for the even for the new materials, you can see new chemical or physical properties, and the materials could be stronger, lighter, or highly soluble. Here, when you see that lighter, you can understand, but when you see that stronger, how can a material that small could be stronger in terms of bulk? So we will see that even with in the physics in nanoscale will be much different, which will be much different than the same for the same material in microscale. So let's look at one example. For example, this is alumina. We can use alumina to make cans, like for example, Coke cans. Or when you look at the nano-alumina, you can see the color is completely changed. Its conductivity change, melting point, reactivity. Most of its properties could change when you go from macro scale to nanoscale. For example, when you look at the nano gold, you see the color is red, but when you look at bulk gold, it's you know the color of gold. So today we will try to understand what could be different from micro to nanoscale, and from this change, what could we gain? So, for example, the volume to one thing here, we can give this as an example: volume to surface area ratio. So, what do you mean by that? So you have let's say you have a cube, and you know the volume of the cube, and you can also calculate the surface area for that cube. For example, let's give an example: 10 centimeter cube. The surface area is 600 centimeters square, volume is 1000 centimeters square, and their ratio, the volume to surface ratio, is 0.6 to 1. So, but here, as objects get smaller, they have much greater surface area to volume ratio. For example, let's go to 2 centimeter cube. The surface area is 24 centimeter, volume is 8 centimeter cube, and their ratio is 3 to 1. So the volume, so here in terms of so when you make these when you make the objects smaller and smaller, the surface area to volume ratio is getting bigger. So which means, so even you have so if instead of using one particle, one object, you can use many objects filling the same volume, but these objects will have much higher surface area. Why is that important? Because if you have more surface, you will have more so you can use more surface to interact between different materials. And if you think about, you have so if you use more materials with more surface area, so you will have more reactions, and you will get a higher signal coming from the materials filling the same volume. So that's why we really want to use nano materials in different applications. So you will feel you will have smaller particles, but these smaller particles, if you sum up many small materials, you will create larger surface area. So you don't have to you don't need any larger volume. With small volumes, you can perform. You can create larger signals using larger surface areas. So this is one of the actually one of the most important reason why we use materials in nanoscale instead of microscale. So it allows us to perform similar experiments in smaller volumes, but with larger interaction areas. So at small sizes, physical properties, magnetic, electrical, or optical properties could change dramatically. For example, let's look at the silver. So by changing the silver or shape of the silver, you can see silver could change its color. It's coming. So last lecture I was talking about the color of light. So the color of light is related to the wavelength of light. So when you change the dimension of the silver particle here, the absorption of its absorption property change. That's why it radiates or scatters different lights when it hits by a white light. So this is one of the one good example that shows that if you change the dimension of a nanomaterial, its optical property could alter dramatically. So here I would like to give you the definition of the nanomaterials. So nanomaterials and biological structures are of the same size, which allows for unique interactions between biological systems and synthetic materials for analytical, diagnostic, and therapeutic applications. So these materials allows you to understand the pathways in biological materials or biological systems. By penetrating inside those biological systems, get reactions with those systems, and allows you to monitor their properties. These properties could be chemical or optical or electrical. That allows you to understand what is really going on in that biological systems. So novel nano and biomaterials and nano devices are fabricated and controlled by nanotechnology tools and techniques which investigate and tune properties, responses, and functions of living and non-living matter at size below 100 nanometers. So nanomaterials allow if you see the word nanomaterials, so it means that materials has the flexibility for you to manipulate the matter and its properties in the size below 100 nanometer. So there are different types of nanometers. I'm going to give you some examples. So backpole. So these are molecules containing carbon atoms bonding together to hollow sphere. Nanoparticles. So these are small particles that could contain single element or the compound of different elements. Carbon nanotubes. So these are like long wires. There are also quantum dots with different colors based on their quantum properties. Let's get here maybe more deep into the carbon structures. So there are different. So here we have structures, carbon structures in different dimensions. They're one dimensional, two dimensional, or three dimensional. I'm not gonna spend a lot of time here, but these carbon structures in terms of their molecular structures from 1 to 3 dimensional, you can add more properties in it. So different structure and attachment. So one of the and as you see, the carbons is one of the hardest materials, such as diamond. but when you go to graphene, and graphene is very soft and slippery. So these are both carbon-based materials, but one of them is very strong and one of them is very soft. So in terms of how you really define that carbon-based material, you can change their optical, mechanical, electrical properties. So carbon nanotubes, carbon nanotubes is recently took a lot of attentions because they give you a different flexibility in terms of their mechanical properties. Carbon nanotubes are the allotropes of carbon with cylindrical nanostructures, as you see in this figure here. So when we look at their properties, so if you look at here, their properties are very gives you the different opportunities for your applications. So first, they could easily penetrate membranes such as cell walls. So you can so without disturbing the cell wall, they can penetrate in the cell, so then you can monitor their the variations in their properties, and monitoring these variations, you can analyze the cellular pathways without killing the cell or even disturbing the cell. Second, their electrical resistance changes significantly when other molecules attach to the carbon atoms. So that allows you to monitor the properties of materials that are interacting with the carbon nanotubes. So let's say you would like to monitor the interaction between two biomolecules, A and B. And if you tag the molecule B with carbon nanotube and stick A and B together, and then apply electrical potential to this complex, AB complex. So if there is a interaction between A and B, using the carbon nanotubes stick on the molecule B, any interaction between A and B will alter or change the electrical properties of carbon nanotubes. So by determining the change in the electrical properties of carbon nanotube, you can monitor or even control the interaction between A and B. So I'm here describing you how we do ex vivo tests. Ex vivo means any tests performing out of any organ or human body. So externally, by tagging any elements of a reaction with a carbon nanotubes, you can externally monitor interaction between biomolecules. So these two important parameters makes carbon nanotubes very famous for different applications. As you see, their diameter is as small as the 1 nanometer, but their length could be even micron. So their aspect ratio, the ratio between diameter and their length, the ratio between their length to their diameter is very big. When you think about the micro scale, if you make an object which is very soft and very delicate, and if you make it high aspect ratio, it's very easy to break it. Even blowing that material, you can break it. For example, if you create, let's make a wire using a glass, but let's make it 10 micron diameter, but with 1 centimeter length. Even if you blow that glass, you can easily break it because of the aspect ratio. It's not that the glass cannot be that durable. towards the strength of your air blow. But when you go to the non-nano scale, carbon nanotubes, even they're slippery and they're soft, you cannot break them. So there are two types of carbon nanotubes: single volt nanotubes and multi-volt nanotubes. A single volt made of a single rolled graphene layer. It's just single rolled. So these are very hard to synthesize. But they are defect free, which is really good. And most important, their most important property is they don't accumulate in the body. So if you perform any experiment on human body using nanotubes, single volt nanotubes, they're almost hazard free, because they don't really accumulate in any part of the body. But multi-volts, they might be accumulate in the body. So those type of, for example, that cup, and they're like these paper cups, they're like paint in it. So for example, that paint could make you, if you heavily use those paper cups, they can make you in long-term cancer, because those colors, the nanoparticles that gives the color and the motifs in the paper, they can accumulate. They accumulate in the body. So these accumulation of these particles could make you cancer. So that's why multi-volt nanotubes are not that good for the in vivo experiments. In vivo means any experiment performed in body. So multiple nanotubes are made of many graphene layers rolled together. Compared to single volt, it's easy to synthesize, but their purity is not that good, because they could be defect in the multi-volt nanotubes. Compared to, in contrast, single volt nanotubes are defect free. They're pure. So here I will talk about nanoparticles. So there are different types of nanoparticles. So polymeric nanoparticles, organic nanoparticles. There are like metal nanoparticles, oxidized nanoparticles, quantum dots, carbon. So I already told you carbon nanotubes. So there are many different types of particles in nanometer scale that could be used in different applications. For example, here I'm giving you one example. You can use gold or gold, silver type of nanoparticles for analyte attachment or signal amplifiers. For example, let's say you have an electrode and you attach a DNA on top. So if you immobilize nanoparticles with that DNA target, this nanoparticle can amplify the signal that you get it from the DNA targets, so that even you have a low number of DNA on the sensor surface, by amplifying the signal using the nanoparticles, you can you can get that signal from a device. So these nanoparticles could allow you to monitor biomolecules with a higher signal-to-noise ratio. Signal-to-noise ratio means the ratio between the signal coming from your sensor and the noise in the device. So if you increase the signal, compared to noise, you can create a more reliable, if you can obtain more reliable information from your test. These nanoparticles can also allow you to attachment of the biomolecules. For example, gold is one of the best biocompatible material because it stimulate the attachment of biomolecules on its surface, and that's why most of the sensing applications use gold. But with gold, it's hard to, it's expensive, and some of the applications, even you use one material, you cover its surface with gold to make it make the surface ready for any the attachment of biological materials. So let's move forward with, again, gold nanostructures. You see nanostructures, gold nanoparticles could be synthesized in different shapes and sizes. It could be nanoparticles, nanorods, cubes, or nanowires. So in different applications, you might use different nanoparticles in different gold particles. As I told you in my previous lecture, I'm also using, for my biosensing applications, I'm using gold. I'm using gold because of its first biological properties, because it's biocompatible material, but also it has a good optical properties. For example, aluminum or copper has better optical properties in my applications compared to gold, but I'm still using gold because copper or aluminum can get oxidized like just in one day. So the surface, its optical properties could be damaged, and also its surface is bad for any attachment of the biomolecules. That's why many applications you see gold as a metal instead of other noble metals. So here I would like to talk about the analytical tools that helps you to understand nanomaterials. So nanoanalytics is the analytical methods for characterization of nanomaterials. So, for example, I'm showing you optical microscope, SEM-TEM. So, optical microscope can allow you to see structures down to maybe a couple of hundred micron, but SEM allows you to see materials down to nanometer scale. SEM is the scanning electron microscope, so it's like a reflection of light from an object, but instead you use electrons. So with a gun, you send electrons to an object, and the electrons scattered or reflect from that. So it hits the particle and scattered from that particle, and you collect with a detector. You collect that electrons, and from that electrons you image the material in nanometer scale. We also have a TEM. TEM allows you to inside of that nanometer scale, nanometer sized particle. TEM refers to transmission electron microscope instead of scattered. In the SEM, we use scattered. Here we use transmitted electrons. So we have an object again, but now electron does not scattered, but it's passed through, so then we can see inside of that material. So those are some devices that allows you to characterize the materials in nanometer size. Now I would like to show you two methods. So there are hundreds of methods you can create devices in nanometer scale, but these are the two main family. So any type of materials should will lie in one of those categories. So one of them is top down. So it's like slicing or successive cutting of a bulk material to small particles. The second one is bottom up. So building up of material from the bottom, atom by atom or molecule by molecule or cluster by cluster to reach the final object. So this is a brief summary. So in top down, you have a bulk material and you cut it into fragments and you reach the nanoscale structure. In the bottom up, we have even smaller materials like atoms, even smaller materials compared to nanoscale structures. So we have smaller materials, we cluster them, and then by more clustering we reach nanoscale structures. So one example to top down. So for example, in this method, we will create like a pillar, a gold pillar. Here we have a membrane. We create so we cover the surface with a resist, and we perform a lithography and development. So in the lithography, when you perform lithography, you break the bonds, or you so this resist is a polymer, and when you use lithography, you break down the polymer component, or you somehow so with the lithography, the polymer uses structure here. So in the development, you get rid of the region covered with the resist, losing its properties. So when you after the development, you have a hole, and you cover that hole with, and you then you cover the whole surface with gold. So now you have a hole with pillar on bottom, and then you have a resist covered with gold. And when you get rid of the resist with small solvents, with some solvents, so for example acetone or isopropanol, you get rid of the resist and the gold covering the resist, the gold film covering the resist. So what you remains is a pillar on top of that membrane. So now, so this is why we call this top down, because we don't have any gold here, but we have a big gold material, and using that gold material, we create a pillar. In the bottom up technique, we will try. So here we would like to make similar pillar, but now we have nothing on the surface, and we started to synthesize the gold on the surface. So instead of having a bulk of gold and cutting by cutting to create a gold pillar, we have small gold gold molecules, and we synthesize that gold molecules on the surface to create a gold sphere. So this is like a bulk material, bulk film, or bulk gold pillar to small gold pillar. And this one, you have just gold molecules, and you synthesize that gold molecules to make a gold nanoparticle. So with the top down up, so in terms of our final goal, you either choose top down or bottom up approach. So here, as you see, from again top down approach, we have a bulk material, and you you will create and you get nanoparticles with the same material. In the bottom up approach, you have the same material in the molecule form or the atom form to create the nanoparticles. So these are all details about nano materials. Now, maybe we can more focus on the application of nanotechnology. So if you look at this slide, you will see nanotechnology could be used in different application fields: energy, cosmetic coatings, structure, medicine, pharmacy, industry, military, even in computer engineering. Like the best example could be the resistors in your processors of computers. So more applications, examples. So we can, for example, in terms of like materials, stain resistant coats. So maybe you see that on internet. There's recently they developed clothes. You cannot really stain them. It's easy to clean. It's like a self-cleaning clothes. In healthcare, people use nanotechnology or nanomaterials for sensing technologies, for drug discovery technology, for drug discovery, or even manipulating drug in human body. In computer science, we can use nanotechnology for hardware development, for better data storage and faster computation. For environment, we can have cleaner energy, or we can even clean air with nanotechnology. So let's dig in more for examples. For example, the first example, the stain-resistant clothes. In this clothes, they are actually mimicking the fruits. So you see when you drop water on the surface of the peach, the water molecules, instead of refuse, they start to beat up and roll off. Like they start to get clustered. You see droplet instead of like instead of a liquid flow. So these materials exactly mimic that the fruits. So here they use nanofibers to create cushion of air around fabric. So they use 10 nanometers size carbon whiskers bound with cotton. So this, again, acts like a peach fuzz, and that's why the liquid rolls off. Here you see in the figure, it's a fabric. It's actually already developed. It's a fabric with water, cranberry juice. Here vegetable oil, even like water. It's different. So the liquid with different viscosity, they don't really stain. Vegetable oil, mustard, for 30 minutes. So when you look at higher viscosity, they make a little bit strain on the fabric, but the cranberry juice, there are no strain on the fabric. We can use nanomaterials, for example, covering surface for protection, covering, for example, here for cars, nanopaint. They use those nanopaints for repelling water, dirt. So there are recently they developed a film. They cover the windows of that film. So in the rainy days, water does not stick on the glass, and it's flows, and also these films eliminates the fog. So you don't need to clean that glass in a rainy or foggy day. So it's the surface, it's with using that protective nano paint, you can make that surface moist free. So I also add a note here in the feature, even this nano paint or nano material could be used to self-repair cars. It could be more, it's futuristic, but this could be doable. So so could change color. I put it in the feature, but recently I saw in one of the videos, they cover the surface of a car with nanomaterials, and the nanomaterial change its color by looking at the different reflection. This is coming from the optical properties of that nanomaterial, and with sending the light with different angles, the scattered light from that nanomaterial is changing. So looking at different angles, you see a different colors, different car colors. We can also clean air using nanoparticles because so the quality of air is coming from a calculation. From that calculation, we determine the number of particles in air. So using a nano paint on buildings, we could reduce pollution. So for example, when we expose when exposed to ultraviolet light, titanium dioxide nanoparticles in paint breakdown in nanoparticles could break down organic or inorganic pollutants that wash off in the rain. So using that nanoparticles, we can decrease the number of particles, the pollutant particles in air. For environment, we can also create clean energy using nanosolar. Nanosolar, so this could be, so why we would like to use solar energy. So compared to classical solar panels, a panel that also combines classical technology with nanomaterials can absorb more photons or more light. In other words, it can create more energy compared to classical solar panels. So from my PhD studies, one of my friends, he was working on nano chip technology that allows more energy to be stored in solar panels. So then with using very similar solar panels, you can create more energy, you can store more energy, so that everybody can, using those very tiny solar panel, everybody can produce its own energy. And for example, I'm talking about like military personnel for a long distance duty. They don't have to carry a lot of batteries, because you know, when you look at a soldier, they carry huge bags, and those bags actually has a lot of like those batteries, because they have different devices. They need electricity. So this could be could help store more energy for cleaner to create more cleaner energy compared to classical technologies. We can so here, this is a fun part of this nanotechnology. We can build smaller devices and chips. So here, for example, Mona Lisa in 8 micron. So this is 8 micron tall. 8 micron is like 10 times smaller than the thickness of a human hair. So they could paint Mona Lisa in a using AFM nanolithography. AFM is atomic force microscopy, so it's you literally touch and sense the atoms of a film in atom by atom precision. We can use healthcare. We can use nanotechnology in healthcare, nanomaterials in healthcare. We can use either use them as like a drug delivery materials, like in vivo approaches, or we can use these materials to amplify the signal of the classical devices to create more reliable information. We can also characterize devices used in healthcare too. So in more detail, we can use nanotechnology in drug delivery, cancer diagnostics, therapeutic application. Therapeutic applications means in any application, including drugs, drugs for treatment, cell repair, or blood clotting. So this is one example that for nanotechnology application in disease detection. As you remember from my previous lecture, I'm also using nanotechnology for disease detection. I'm using chips, nanometer size structures to detect pathogens like bacteria or virus, or small proteins that are related to a particular disease. So here one example for nanotechnology for disease detection. Here they use a quantum dots glowing so here UV light. So they so the quantum dots penetrate into mice and the tumor. So here they can use the quantum dots to see the tumor, the location of the tumor. Here they used quantum dots in different shapes and sizes. These quantum dots contain free electrons and emit photons. So using this photon emitting from the quantum dots, they can precisely locate the tumor on the mice. And these colors are coming, and as I told you before, the color is coming from the shape and size of the materials, the nanomaterials. Here, another example in healthcare, but now nanofibers nanofibers are used to repair the heart muscle. Here they use mimic the filaments in the muscle and replacing the filament with the heart, replacing filament in the heart muscle with the nanofibers. You can repair the muscle. Here in the figure, you see the cardiac tissue grown with the help of nanofiber filaments. This is pretty much the same type of aim, the goal I'm pursuing in my lab. Here, we can, as you see in the slide, we can prevent viruses from infecting human by coating the viruses, actually coating the proteins on the virus. You could stop viruses binding to cell. So actually, this is preventing. This is a way. This is a futuristic way to prevent virus infects. This is a way to infect. The way to prevent viruses, prevent the human body and infect us. This is one of the fancy example for the nanotechnology. So nano robots could help us to monitor the pathways inside the body, or they can monitor the location. They can determine the location of the cancer, the tumor or tumor in cell body using an external effect. So they can. There are more in detail. You can use nanobots to clear clogs in veins or arteries. Nowadays we do these physically, reach these clogs inside the veins and clean it with a wire. You can maybe in the future we can use those nanorobots to so we can send these nanobots to the problematic spots in the veins with it like a targeted delivery. So we will send directly that we can send these nanorobots directly to the veins to unclog it. The robot is designed to move inside arteries, guided by an indigenous developed a movement control algorithm. So we can externally control the position. We can the motion of that nanorobots to effectively reach that clogged spot in the veins. We can use these nanomaterials to cleaning our mouth. This is also a good example for application of nanomaterials in human health. Here, for example, a mouthwash full of smart nano machines could identify and destroy bacteria while allowing the harmless flora of the mouth to flourish in the health ecosystem. There are some groups also, they're developing smart contact lenses that gives, so they monitor the glucose level using a smart lenses. So why we really need for that? Because the best way to determine the glucose level is from the eye. So these nanoparticles in that contact lens can react with the glucose molecule present in the rear tears, and it gives you and it determine the glucose level directly from that tear using the chemical reaction. So this is, I think it's been already released that as a commercial product. That's what I know. We can also use films that are like flexible films to monitor and attach to our skin to monitor any to monitor our healthcare using our sweat. So these flexible, lightweight films could be in the future to monitor some health problems that could be determined using the variations in the sweat. So here, till that now, I focused on the pros or the positive sides of the nanomaterials, but maybe after, so here we might start to talk about any problems or hazards, both human or nature, due to nanoscale sized objects. So First, nano devices are sensitive. The radiation particles can cause fatal defects. So the so development of these nanomaterials requires very clean environments. So redundant copies compensate for high defect rate. So when you would like to, when you develop a nanomaterial, so some of the, I also in my grad school, I also worked in the clean room. So since the nanomaterials are very small in size, anything on air could really affect your fabrication procedure badly. Let's say, let's give it like a small example. For example, I was fabricating nano holes or nano apertures in the diameter of 200 nanometer, but a dust in air could be even as big as a micron. So it's like 5 times bigger than the size of the the nano chips that I'm using, the nanomaterials I'm developing. So the environment that I was developing these nanotechnology has to be a dust-free environment. So you have so one of the most important problems for those clean room environment is you have to they need a lot of filters, they need highly sophisticated infrastructure, so you need a lot of energy, like electricity. You also use a lot of chemicals that can harm to nature. So yes, the application, the outcome of the nano devices is very critical for technology or even human health, but you have to be precise, and you don't need, you shouldn't, you have to be careful to fabricate or create those nanomaterials or nano devices in nanometer size. And so to eliminate the redundant copies, that increase the risk to pollute to nature and use unnecessary energy. These type of pros, even you have critical technology, you have to also consider those type of effects that might harm to nature. So potential risks, let's continue with that. The environmental issues, nanoparticles could accumulate soil, water, plants, even human body. So new risks, so that's why new risk assessments methods are needed. So those assessments should eliminate this accumulation and also should eliminate these materials pollute the air and also soil. In addition to harm to nature, this could also, these particle accumulation could also cause health problems. Nanoparticles could be inhaled, swallowed, absorbed through skin, or you can even get those nanomaterials with food. The airborne nanoparticles could be inhaled. And inhaled nanoparticles could enter the bloodstream, and certain nanomaterials even could cause rapid and persistent pulmonary fibrosis and cardiovascular dysfunction. So these are all how. So from small sickness to even cancer, like very deathful problems. So in order to diminish these problems due to nanomaterials, we have to be careful while we are creating this technology, and also while we are using those technologies. More like these are some detailed examples. So these nanoparticles these particles are classified by international agents for research on cancer. As I told you, the accumulation of these particles could in long term could make you cancer. So when you look at human body, these schematic shows you some of the major toxic effects that can be induced by the nanoparticles. These effects can categorize as the damage to tissues, cells, and even molecular scale. So in summary, yes, we have nanotechnology has a lot of advantages. Renewable energy, extend the limits of electronics, allows you the drug discovery, treatment methods, but it has also a lot of disadvantages. It damage the nature. It could damage human health. There are some sociological impacts. It has an impact on the job market. It could destroy some of the jobs, some classical jobs. It can compromise the safety, the properties of this technology, could facilitate espionage. It also triggers the production of nanoweapons or biological weapons. So in summary, science at nanoscale. So I will try to sum up everything here. So nanotechnology integrates chemistry, physics, biology, materials engineering, earth science, pretty much every physical sciences nanotechnology penetrated. With the use of nanotechnology, we have the power to control data and manipulate these nanoparticles in very tiny scale. And this manipulation in nanometer size, new areas of research and technology design, we open doors for new areas of research and technology design, better understanding of matter interaction, matter interaction, new ways to tackle important problems in healthcare, energy, environment, technology. So with the use of nanoscale, we can speed up development in classical technologies, but in the meantime, we also have to consider some hazardous outcomes while we create this problem. So we have to somehow balance the nanoscale, so the outcome from the nanoscale and their hazardous output, to create cleaner, safer energies, both human and the mother nature. So here then I will stop and can take your questions.
Thank you very much,
Sure.
Dr. Arif, for the incredible talk that already started from what is the nanotechnology and how we analyze that, the use of the nanotechnology itself, especially also in the sensor and the analytical or in the sensor field, and also talking about some impact, which actually is maybe less known, or I mean, it's not usually discussed in the class or maybe in the talk, because as you mentioned, they have some negative impacts, especially on the nature and the health, and also on the job. This is the first time I heard about the job. That's very interesting.
Because when you create new jobs, like when you speed up some processes, then some people will lose their job. So, yeah,
because
classically,
their part is not needed anymore.
yeah, you don't need them anymore. Yep.
Yeah, I see. Okay, so okay, so we will have first a question from Muhammad Ihda. So Ihda, you maybe can speak.
Okay, Pak Irham, thank you for the time.
Sure.
There is my voice.
Yes,
yes, yeah.
Okay, sir. Thank you for your presentation. So I
Thanks.
will ask about something. Can you explain about the factor that make various shape of nano, and what does this shape depend on? Yes.
I lose the word. I couldn't hear
Yeah,
you.
what I also cannot hear what nano, Ihda.
Can you explain about the factor that make various shape of nano? So the factor that make nano have various shape.
It's the line is pretty bad. Can you type your question?
Maybe you can type the word.
Yeah, the voice.
Ihda.
Yeah, the voice is getting.
I think he asking about the factor to make something nano.
Yes. Yeah, I got that, but that part is all missing. Yeah, can you write it? Yes.
I think maybe we can go to another question first with from Indrika Novella. Maybe you.
Yes. Thank you. I want to ask to Dr. Arif. We know that usually material in nanoscale tend to agglomerate, so that will affect the application of the nanomaterial. So what should we do to prevent or to avoid the agglomeration in the nanoparticle? Okay, can you?
Yeah. So there are some. So yes, materials they tend to make. So they tend to make cluster, right? So there's some either physical or chemical. Like some they're like they have physical or chemical affinity between those. So you would so your question was how to eliminate their clustering, right? To make yes. All right. Yeah, there are some ways to do that. If it is chemical, so for example, so the best way is to use some coating for those. One thing could be coat those materials so then they don't attach each other, or they because they will tend to so they will tend to have a reaction with each other. So when I first think about a problem like this, I also have some similar problem when I use nanomaterials. The first problem is, for example, when think about a nanoparticle, if you see a lot of clustering of that nanoparticle, one thing is you might check the concentration. You know, if you use too much concentration, you see a lot of clustering. One problem is that. Second, you have to definitely follow the protocol as best as you can. For example, even in my lab, sometimes students come to me and then look at when we look at their particles, when we look at their the solutions, we see a lot of clustering. The reason of that clustering is sometimes they don't really steer their solutions. You know, so there are different steps in their protocol, and the most easiest step of the protocol is the steering of you know, or vortex their structure. This is allows you to eliminate those clusters in your protocol, in your solution. So the second is, you have to be careful with your protocol. The first one is, there are some the first one again, there are some coating agents that helps you to eliminate those those clustering. I'm also sometimes using those. Sometimes I use those agents. For example, one example, those agents is PLL. For example, PLL allows you to make a smooth surface so you can make the surface as slippery as you want, so then two nanoparticles, they don't attach each other. This one could be also help you to eliminate those clustering. I am thinking a more solution to those. Ikram, do you have any suggestion?
About what?
Yeah, so to eliminate the clustering of nanomaterials.
Yeah, I'm also not really sure.
Yeah, so they're
It really
actually
depends.
depend on the materials, but
It depends on the material. Yeah, that's
yeah, but coating these materials is one way. Second, performing the protocol as best as you can. Believe me, in my lab, so sometimes we cannot get rid of those clustering, but and then we realize that we either use a huge number of particles, we don't really steer them well enough to make a homogeneous solution, or even you perform all those and it doesn't really help you. The best way is to cover the surface of that material, so then they don't attach each other. We can go to the next question.
Yes, I think we can go. We can come back to the question from Ida, that he asking that what about the factor that make a various shape of nanomaterials usually?
Which one? Ida, right? Can you explain about the factor that make various shape of nano? What does this shape depend on? Can you explain about the factor that make various shape of?
So
how it says how you create this shapes, right?
Yes.
Okay. How you okay. So it depends on how you create them. It depends on the method you create them. For example, if you would like to create a triangle shape in a top-down approach, you use a mask with the triangle shape that helps you to create a triangle shape at the end of your product. So in the bottom-up shape, it's completely different. How you so in the bottom-up, you create from the bottom the molecules. And you started to cluster in the shape you want. So the way you shape the cluster of the materials define the final shape. This is how you define the shape. The reason why we create different shapes, the reason we create different shapes, because the shape and the size define their properties. So if you remember the color of the mice I showed you, different shapes gives you different colors. That means different shapes provides different optical properties from the same materials. Did I explain your question? Answer your question?
Ida, maybe. Yes, he said.
Okay, all right. I mean, I answered two. I gave you two answers. I think one of them is
I think more
providing your excellent. Okay.
More or less give some
okay.
imagination.
Yeah, one of them was answering his question. All right.
Yeah, I think one of them also. So
okay. All right.
Maybe we go to another question. Is that okay with you?
Sure. Let's go.
Okay, about question from Widardo. Can Widardo speak for yourself about the question?
Sure.
Please.
Excuse me, sir. My name is Vidarto. Thank you for the lecture.
Sure.
As we know, titanium oxide is used for photocatalysis for degrading dye in water. So my question is, if titanium oxide used in paint, won't it degrade?
Titanium oxide. All right. So titanium oxide is used for photocatalyst, yes, in water, yes, to decompose dye. If titanium oxide uses paint, mix a paint, won't it decompose the paints? Oh, okay. Mix, decompose the paint dye. Oh. Well, yes, it's decomposed dye, but what do you mean by paint mix? What is? Oh, okay. You mean?
I think he means about the you talk about the paint. On using nanoparticle in the paint or something.
Oh, okay. So
he is actually asking about another topic about the photocatalytic part.
Oh, okay. Yes, I'm not sure.
This one.
Did I say anything about titanium? Right.
This one.
I said.
Yeah, he's in here. He imagined that the titanium dioxide is breaking down the organic compound. So
yeah,
isn't it will be also degrading the paint itself because the paint itself is some organic and inorganic compound.
Oh, okay.
Interesting question, but maybe
it's you can use it for decomposed dye, but the paint, organic and inorganic. So it's the mixture. The paint is the mixture of both. So it might. It's a good question.
Yeah, this is a good question. Maybe.
Yeah. Titanium oxide used as a paint mix, won't it decompose the paint itself? The paint is it doesn't have to decompose because the paint is combination of different materials. So we cannot say it's decompose the paint at all, right? It's because it's a mixture of many materials. Yes, you may damage it, but I don't think you can completely remove or decompose the paint.
Yes.
Because it's a mixture of many materials, right?
Maybe yes, and also because usually it needs waters to.
Yes, it's
as long as this doesn't contact with the waters, I think should be okay. And maybe the water itself, the radical also will be only in the water, so it will be not covering the paint itself. Maybe if I can add, so that's what maybe less possibility that it will be breaking the paint itself instead of organic that is on the surface. Of the paint.
But it might give us small damage, but not all of them.
Maybe not
all of them.
So big damage. And because of that, you say that it's also mix of a lot of compounds. It's not so easy to break down.
Yeah.
So I think that's it about the question. Widardo is okay.
Yes, sir. I understand it.
Okay.
Thank you for the question.
You're welcome, sir.
Yeah.
Thank you.
And maybe
Devi, I think.
Maybe the one that raising hand, Nur Aziza.
Nur.
Maybe you can speak.
Okay. Thank you, Pak Irham, for the time, and thank you, Dr. Arif, for your explanation about nanotechnology. It is so interesting, I think, and also it is related to my thesis research, which I use nanoparticles too, that I have synthesized on my undergraduate thesis.
and I'm going to continue with its application on electrochemical nanosensor. I have some questions. So the first one is there a reagent or a medium or maybe we call it a template that can be used to increase the performance of nanoparticles in their application on nanosensors? And the second one is which type of sensor method that can provide the best performance in the application of nanoparticles in nanosensor? Is it an electrochemical sensor or biosensor or optical biosensor that have discussed on the last week? So yeah, that's all of my question. Thank you, sir.
Okay. So it's a very general question because it depends on the application you use. So in some of, so if you would like to, so some of the problems you might would like to look at the electrical properties and some of them optical properties. It really depends on the biological reaction you would like to monitor. So it's not so the way we talk about so there is no specific answer to best application for the nanomaterial. It's so the biosensors are they're developed based on the problem. So let's say that there are problem specific. So based on the problem, you first choose whether you go with the electrochemical properties or optical properties, because some of the biological problems you cannot really apply optical electrochemical biosensors. So, but in broad perspective, what you can say is first. So if you're performing electrochemical biosensors, first you have to decide whether that biological problem can fit your analytical method or not. All right. So you cannot really say, oh, optical biosensors are the best because of this, because all biosensor approaches have their own capabilities, and you cannot really compare electrochemical biosensors or optical biosensors based on one biological problem. So if you are developing, so I'm developing optical biosensors, and Professor Yeni there, she's developing electrochemical biosensors, and we know the capability of our technologies. Either in one particular problem, her method is better, or in another problem, my method is better. But what I can tell you is nanomaterial definitely helps you to increase the signal of your biosensing technology. So for example, if you tag, so for example, you are developing a DNA biosensor using an electrochemical device. So if you tag the probe or DNA sample with your with a nanomaterial or a nanoparticle, it allows you to increase the signal coming from your electrodes. So then with the same number of biological material, you will get more signal. More signal means even a small number of biological material, you can still create a signal from that biological material. So that gives you high resolution signal or more reliable signal, because for example, if you don't use that particle, then at some, so the number of biological material you can detect with your technology will be maybe I can make it more simpler. The number of biological material that can be detected with your sensing technology should be higher to get enough signal. So nanomaterial helps you to get enough signal even with the small number of material, so then you can increase the limit of, so you can decrease the limit of detection or the number of or the concentration of your analyte that you can detect with your electrochemical biosensor. So these nanomaterials helps you to get more signal, so then you can create more reliable information from the analyte under investigation. So you cannot really say this sensor is better than this and this material is suitable for this and this. This is the question is whether my method is suitable for this particular problem or not. Then nanomaterial, and then you use nanomaterial to improve the properties of your material. So when you first, so if you want to improve an electrochemical biosensor, first thing you have to ask is whether your technology is suitable for that problem or not, instead of comparing different techniques. Is it answering your question?
Yeah, it really answered the question. Thank you so much.
Thank you.
Sir.
Thanks. Thank
Yeah.
you.
Thank you for the question and also the answer. It's very interesting discussion. And we have another question, maybe 1 or 2 questions. Is that okay with you?
Okay, sure.
So,
Nanomaterials used for growing tissue to repair hearts. I think it's good.
We have one question that is a little bit.
Oh, okay.
Is that okay?
Okay.
Maybe
Sure.
Mela, can you talk about the question?
Yeah, thank you. I want to ask something about nanomaterial, which has different structure, but same size. But nanomaterial has different color or visible light. Maybe for silver in this presentation, how that thing can happen? Maybe a relationship between nanostructure and visible light absorption.
I couldn't hear the question. Can Ikram, did you?
Yeah, is actually asking about the different color of the nanomaterials that, for example, in her example is, for example, silver. Like you can have the same silver, but you can have some different color of the silver itself.
Okay, so why is the reason?
Why this is happened? Maybe because of the structure and the visible.
Okay. So with the same material, she was referring. I think. Let's go there. I think she was referring something like this, right? What is this color coming from? Yes. So the color is coming from the wavelength of light. So when you change the size or dimension of the nanoparticles, it reflects or scattered is a better terminology here. It scattered the light in different wavelength, and the wavelength is directly related to the color of light. So for example, let's forget about the shape here. For example, let's think about that gold nanoparticle. If you increase the diameter of the nanoparticle, it scattered the wavelength, it scattered the light with larger wavelength. So from smaller diameter to larger diameter, you will see either blue, green, yellow, or red. So it related to the diameter relates to the scattering wavelength. Scattering wavelength is directly related to the color of the light.
Okay.
Okay.
Is that answering your question, Mela?
Yeah, but I asked about silver, that in this slide, silver nanoprism and silver spheric in 100 nanometers has different color but has same size,
same dimension. Yes. So yeah, you can give the example from the
between the structure.
So so if you have a same shape, increasing the dimension gives you different color, for the different size, changing the shape also gives you different color. A triangle, for example, a triangle and sphere gives you, they can scattered the wavelength source. They triangle and sphere, it can scatter the light with different wavelengths. Also they can give you different color. So two parameters is important here. Not only shape but also the size. So you can model the scattering wavelength using both parameters. Yes, it's two. So here, for example, where is that? Sphere,
Nanoprism, and this one. Yes.
Yeah. Two different rectangle. For example, you have a rectangle and triangle and sphere with same sizes. They will scatter light in different wavelength.
Yeah.
Yeah,
So,
you can also use shape too.
Yeah, so it's actually similar with the effect of this different size, because at the end, the scattering is the one that give us the lights, the particles, right? Yeah, so
scattering frequency or wavelength is changing with shape and size.
Yeah. So did you get the answer, Mela? More or less.
Yes. Thank you, sir.
Thank you.
Thank you very much. Also, a very good question, I think.
Yeah.
Very interesting question. So I think about the time is already finished, but
okay.
We still have two questions. Maybe they can email,
question,
or you want to answer? Maybe I don't know.
Which one is the? Let's answer.
The one that growing tissue to repair hearts using
okay.
And the drug, about the nanoparticle drugs. Can we turn certain drugs into nanoparticle? About the bioavailability.
Okay, thank you. I would like to ask, can we turn certain drug into nanoparticle? Does the change in size can affect the bioavailability and solubility? Can we turn certain drug into nanoparticle? What does that mean? We can use nanoparticle with the drugs. In those therapies, we use nanoparticle either to deliver the drug in the particular spot or monitor, or we can so after the drug treatment, we send these nanoparticles to the certain spot in our body to monitor the effect of this drug. We use nanoparticles in either this two way, but this is not can we turn certain drug into nanoparticle? No. This is not. This is what we do. So we either tag drug into nanoparticle and send it to the location the spot that we would like to treat, or we send nanoparticle itself to that spot to monitor the effect of the drug.
Okay, so that's the more or less the question and answer. And another one is about nanomaterial to growing tissue to repair hearts.
Growing tissue to repair hearts, I think it could harm the patients if it is still there once the heart is recovered. No, this is not to recover the muscles, because this muscle is already the muscles are already gone. So we try to repair it, and also the other thing is, even if it is the case, we can repair those parts with these soluble nanomaterials. For example, let's think about one-dimensional the carbons. It is soluble. It doesn't it, and they don't accumulate in human body. But this is, I don't think no one really, this is just an example that it's a futuristic example. It was done in the lab, but this is a great example how we can really replace the damaged part in our human body with a nanomaterial to repair those tissues, because some of the tissues it takes forever to repair. For example, the elder people, that it takes ages to really repair the tissues. So to increase their life quality, it's a great idea to repair those with those nanomaterials, with the nanomaterials.
Yeah. Okay. Thank you very much, Dr. Arif, for all of
Thanks.
answers. I think the student will be so happy about your answer. And of course, we also would like to thank you for your times for these 2 weeks. Which is very interesting. Even for me, I have a lot to learn from your.
Thanks a lot. It was my honor to. Yeah, it was an honor for me to give lecture.
Thank you very much. Yeah,
thank you too.
The students also said it's very interesting pack of information, which
thank you a lot. Thanks a lot.
Can stimulate their willing for learning about the sensor and the nanomaterial and the optical things. Okay, so once again, maybe we can just give small applause for the for the talk. Thank you very much.
Thank you.
So we hope we can see you again sooner or later. Maybe.
Sure.
Yeah, maybe Professor Yenny will contact you again later for more of things.
All right.
So yeah, once again, thank you very much, Dr. Arif, and I think we will close the session.
Thank you.
So see you later. See you again.
See you. Good evening. Bye bye.
Yeah, good evening. Good afternoon. Bye.
Yeah. Bye bye.